Hello everyone, this is a practice session, revision session on statistical mechanics. We will be seeing questions that usually come in statistical mechanics. We had done a one-shot revision, but I don't think that one-shot revision will be enough for statistical mechanics, considering the fact that we really need to solve some questions in order to get the idea of it. Okay, so write down first question. Consider a statistical mechanics. Consider a system of n non-interacting spin half particles, each having a magnetic moment mu is in a magnetic field is in a magnetic field B is equal to Bz cap if E is the total energy of the system. E is the total energy of the system. Then number of accessible microstates. Number of accessible microstates is equal to how much? If you consider a system of n non-interacting spinor particles each having a magnetic moment mu is in a magnetic field B is equal to Bz cap. So if E is the total energy of the system, the number of accessible microstates is. In non-interacting spinor particles each having a magnetic moment mu is in a magnetic field B is equal to Bz cap. If E is the total energy of the system, the number of accessible microstates is. Okay. Non-interacting spinor particles each having a magnetic moment mu is in a magnetic field B is equal to Bz cap. E is the total energy of the system, number of accessible microstates. So there is spin half. So for example, this is spin up. The magnetic field direction is Bz cap. Spin up and there is spin down. So spin up. Okay, these are in same direction. We know potential energy is minus mu dot B. As they are in same direction, this would be minus mu B. These are in opposite direction. Magnetic field upward, downward is the spin. So U is equal to minus mu dot B cos pi, that is minus 1, that is mu B. Okay, opposite direction mu B. Okay, so total number of spinor particles is how much? N. So N is your total number of spinor particles. Alright. So suppose n small n are the number of up spin. Okay. Hello. How is n is the number of spin up and n is n minus n will be the number of spin down. Okay. So can you write the equation for now for the energy? Okay. Can you write? Please try. I'm just coming in 1 minute. Okay, so small n number of particles are spin up, n minus n are spin down. So total energy will be n into minus mu v, because minus mu v is the spin up particle energy, plus mu v is n plus n plus mu v is equal to E. Right? I can write it as minus n mu v plus n mu v minus n mu v is equal to E, which implies minus 2n mu b plus n mu b is equal to E, isn't it? Right? So I can say uh, minus 2n, right? 2n mu b is equal to n mu b minus E. Okay. Now what is small n? We have to calculate small n from here. Small n will be 1 by 2 mu b n mu b minus E. Okay. 1 by 2 mu b n mu b minus b. Right. So I will divide this mu b inside n mu b by mu b minus E by mu b. So that will be half n minus E mu b. That will be small n. This is a small n. Alright. Now what is n minus n then? N minus n will be n minus half n minus E by mu b. That is n minus half n plus E by 2 mu b. Okay. N minus half is n by 2 plus E by 2 mu v. Is that right? E by 2 mu v. This is your n minus n. Hmm. So if you see, your small n is this, your n minus n is this. Alright. What is the question now? Question is number of accessible microstates. Number of accessible microstates is the question. Number of accessible microstates. So the formula for it is what? Microstates. Omega is equal to ncn, isn't it? That is n factorial by n factorial n minus n factorial. Okay. So n is what? N is as usual n. Now n small n, we just calculated this, half n minus half n minus e by mu b factorial. All right. Into n minus n is this n by 2 n by 2 plus e by 2 mu b factorial. All right. So this is so let's take this half out. If I take this half out, this half they will they go out, become 1 by 4. So 1 n factorial by 1 by 4 n by n minus e by mu v factorial into n plus e by mu v factorial. Okay, that will be the answer for number of microstates. I hope you understood. I hope you understood this question. A very good question, and you just have to be a bit like you need practice to solve this kind of questions. What I did here, number spin up particles are given, and there is a magnetic field also given. So spin up particle, it can be spin up, it can be spin down. It's not like always spin up. So spin up energy is minus mu dot b, that is minus mu b, because minus mu b cos theta, theta is 0 degrees, so minus mu b. Here it is mu b. Then what? N, for example, small n number of particles are spin up, n minus n are spin down. Okay. We just, the spin of particle energy is minus mu v, spin down at mu v. So total energy will be what? This into this, like this plus this. So small n into minus mu v plus n minus n into mu v. So this is the total energy now. After that, I calculated small n. Why I calculated small n? Because I also need n minus n. Why do I need even n and small n? Because our number of microstates is ncn, so we will need these terms n minus n and n in the expression of here, because this is n factorial by n factorial n minus n factorial. So we need these terms here. So that's why I calculated. And at the end I will just put them here, and this will be answer. You will see this in the options. Okay. Yeah. I hope you understood. Okay, next question. Question number two. Question number two. Consider two systems. Consider two systems A and B, each having each having two distinguishable particles. Each having two distinguishable particles. Each having two distinguishable particles. In both systems, in both systems, in both systems, each particle can both system each particle can exist in exist in states of energies, zero, 1, 2, 3 units with equal probability, the total energy the total energy of the system is 5 units. The total energy of the system is 5 units. Okay. A has 3 units, A is 3 units, and B is 2 units. So entropy of the system is how much? Of the system Entropy of the system is how much? Consider two systems A and B, each having two distinguishable particles. In both systems, each particle can exist in states of energy zero, 1, 2, 3 units with equal probability. The total energy of the system is 5 units. A is 3 units and B is 2 units. Entropy of the system. Okay, two systems A and B having distinguishable particles. Right, having distinguishable particles. Okay. Let's try this question first. A is 3 units. Okay. How can we solve this question? Two systems A and B. This is system A. This is a system B. Their unit energies are zero, 1, 2, 3. 0, 1, 2, 0, 1, 2, 3. Okay. Let's make some boxes like this so that we can arrange the particles. Alright. So how many total energy of the system is 5 units. Right. A is 3 units, B is 2 units. So A should be 3 and B should be 2. Suppose, yeah, this is also 0, 1, 2, 3. 0, 1, 2, 3. We'll arrange the particles here. So two particles in the system, two systems having two distinguishable particles. Suppose two distinguishable particles are X and Y. Suppose. So here how can we arrange it so that we will get 3 units in A. So X, Y, yeah, Y, X, 0, 3, 3. Now X, Y, Y, X can do that. So I can do that, right? Yeah. So I think that this much only, right? So both system can exist in states of energies with equal probability. The total energy of the system is 5 units. Yeah. So this much only can possible. 1, 3, 4. Yeah. So here if you see number of microstates is this is 1, 2, 3, 4, where all the energies are 3, 3, 3. So the number of microstates in A is 4. 1, 2, 3, 4. Now for B, the total the units is B is 2 units. Let's see. This is XY, hmm, XY, right? XY, isn't it? XY only, right? Any other? Any other? No. Because see here we could not take 2 because see this is 3 units. So 3 is kind of odd. So we cannot make 2 here. 1 this is XY, this will be 2. XY this will be 4. So it's not possible. So here only it's possible because this is an even number. So I could put 2 here. So see 1, 2, 3. Any other combination is not possible. So omega B is your 3. Okay. Omega B is your 3. So number of microstates A is 4. Number of microstates in B is 3. Okay. So if you see total number of microstates is actually this is a like it will be multiplied. Okay, it will be multiplied. So 4 into 3, that is your 12. So number of total microstates is 12. So what is the question? Question is entropy of the system. Entropy of the system. So entropy is what? We know entropy is S is equal to KB ln omega. So simple KB ln 12. Okay, this is the answer. It's not that hard. Just have to do it properly. Need a bit of practice though. Suppose this question was asked in another way. Suppose the question was, this is what given, two distinguishable particles. Suppose exactly this question is asked, but the question is indistinguishable particles. Two indistinguishable particles. There are two indistinguishable particles, okay, in two systems A and B, where the total energy is 5 units. A has 3, B has 2. Okay, so arrange. So what is the total entropy now? Okay, again let's do the same thing for A. This is for A. Sorry, 0, 1, 2, 3. A should be 3 units, and this is a B. B should be 2 units. Okay, 0, 1, 2, 3. So two indistinguishable, we can take just like this. Okay, we don't need to make it XY because XY are distinguishable. This is indistinguishable. We cannot recognize them. Okay, so total energy is 3. So one would be here, one would be here. We cannot interchange it because these are indistinguishable. I cannot put this here, put this here. I cannot distinguish between them that which is which one. So it's just one. Now this one here, this one here. Right, that's it. That would be it because I cannot make any more configuration because these are indistinguishable. So this is one state, this is two. So your my number of microstates in A is 2. Here then, this is one. Again, this is one. So there is no other configuration here. So number of microstates in B is 2. So total number of microstates is omega A into omega B. That is 2 into 2. That is 4. So now the entropy is what? Ln Kb ln omega. That is Kb ln. Okay, is that right? That's the answer. This is how questions come in an exam. So better prepare yourself for this kind of questions. Alright. Okay. Let's move to the next question. Question number 4. Partition function is given. Partition function of an ensemble at temperature T is given by Z is equal to 2 cos h epsilon by kBt to the power n. Okay. So what will be the heat capacity? What will be the heat capacity of this ensemble at temperature T is equal to epsilon by K? What will be the heat capacity of this ensemble at temperature T is equal to epsilon by K? Okay. So again, partition function is given. Partition function of an ensemble at temperature T is given by Z is equal to this much. What will be the heat capacity of this of this ensemble at T is equal to epsilon by K? Try this question first. Try this question. Try this question. Partition function of an ensemble at temperature T is given by Z is equal to this. What is the heat capacity? See. So partition function Z is 2 cos hyperbolic epsilon by kBt to the power n. Okay. I can write it as 2 cos hyperbolic beta e beta epsilon. Beta is 1 by kBt. Right. So we know average energy for calculating heat capacity. First of all, average energy is minus del by del T L ln Z. Did I miss it something? Del by del beta minus del by del beta of ln Z, which can also be written as kBt square del by del T of ln Z. kBt square del by del T of ln Z we can, because if you want to prove minus del by del beta is 1 by kBt ln Z. See, kb goes up, minus kb by del of 1 by T ln Z. Del 1 by T is how much? Minus 1 by T square del T ln Z. Right. So this goes up and minus minus gets cancelled. So kb T square del by del T of ln Z. Okay. Same thing. Same thing. Okay. So E is equal to what then? kb T square del by del T of ln Z. So kb T square del by del T of ln 2 cos hyperbolic beta, okay, beta hyperbolic epsilon by kBt to the power n. So n, as it is ln, we can take the n out. So n kBt square del by del T of ln 2 cos hyperbolic epsilon by kBt. So this becomes nkbt square into 1 by 2 cos hyperbolic epsilon by kbt. Try to do the derivative yourself. And now into 2 sine hyperbolic derivative of cos hyperbolic sine hyperbolic. There will be no minus. Be careful of that. Into epsilon by kb into minus 1 by t square of 1 by t. Yeah. Yeah. So 2 to cancel. This is what cot hyperbolic n kbt square. Now this is minus epsilon by kbt square cot hyperbolic epsilon by kbt. So this is kbt square cancelled out minus n epsilon cot hyperbolic epsilon by kbt. Okay. Oh, sorry. I'm really my bad. I'm really sorry. Sine by cos is sine tan. Such a basic mistake. Stan. I thought I saw it from this like cos and that's why my bad. Really my bad. Tan hyperbolic. Okay. Um, epsilon by kbt. So this is the average energy. What we need? What is the question again? The question says find the heat capacity. So heat capacity C is equal to d by dt of E, average energy. So d by dt of minus n epsilon tan hyperbolic epsilon by kbt. So minus n epsilon comes out d by dt of tan hyperbolic epsilon by kbt. Is that alright? So minus n epsilon tan hyperbolic derivative is sec square. Sec square hyperbolic epsilon by kbt into epsilon by kb t square. Go inside derivative. Yeah. So this becomes n epsilon square by kb t square. Sec square hyperbolic epsilon by kbt. Is that alright? Is that alright? Now what is given in the question? There is another thing given in the question, that is T. We have to find the heat capacity of this in simple, and T is equal to epsilon by kb. So it's good for you. We can just so when T is equal to epsilon by kb, we just put in place of T epsilon by kb. So this is equal to C, heat capacity, n epsilon square by kb epsilon by kb whole square sec square h epsilon by kb epsilon by kb. Clear? See how easy it is. So this n epsilon square gone, kb sec square 1 sec square hyperbolic 1. Okay, that's it. I don't like we don't know the value of sec square hyperbolic 1, so let's just let it be like this, n kb sec hyperbolic. Okay, this will be written something like this. Alright. Okay, sec hyperbolic square 1. Is that alright? Okay. Hmm. Next question. I hope you understood. Next question, question number 5. Consider a system having consider a system having three energy levels, three energy levels with with energies 0, 2 epsilon and 3 epsilon with degeneracy 2, 2 and 3 respectively, 2, 2 and 3 respectively, 4 bosons of spin Four bosons of spin 0 have to be filled have to be filled filled in these levels, okay, such that the total the total energy of the system is 10 epsilon. The number of waves, what are the number of waves, what is the number of ways to obtain 10 epsilon? That is the question. Consider a system having three energy levels with energies 0, 2 epsilon, 3 epsilon. So it degenerates 2, 2 and 3. Okay. Four bosons of spin 0 have to be filled in this level such that the total energy of the system is 10 epsilon. What is the number of ways to obtain 10 epsilon? That is the question. Alright. So how to solve this question? Four bosons of spin 0. Spin 0. Let's see. For bosons, we know number of microstates. Number of waves means number of microstates. Number of microstates for boson. I have the formula. Bosons omega is equal to pi I ni plus gi minus 1 factorial divided by ni factorial gi minus 1 factorial. This is the like it will be multiplied. So to 0 to epsilon 3 epsilon. So 0 won't count much. So what will we take? 2 epsilon, 3 epsilon. Because 0 won't contribute to your 10 epsilon, right? The total energy should be 10 epsilon. So 2 epsilon suppose, and this is your 3 epsilon. Okay. So for 2 epsilon, what is the degeneracy? 2. Okay. 2 epsilon is degeneracy is 2. So 2 epsilon degeneracy is 2. What are the number of particles here? See, this is 2. Okay. Now N2. This is N2. N2 is what? 3. And degeneracy is what? Hmm? Because see, this is epsilon epsilon making 2 epsilon, right? So n is equal to 2. This is epsilon epsilon, so n is 3. And degeneracy is what? It's given. Degeneracy is given 3. Degeneracy is given 3 here. So if I, okay, sorry, n will be, oh, only n 2 can be here. You see, if I put 2 particles here, that will be what? 2 particles here, suppose. That will be what? 2 plus 2, 4 epsilon. So what is left? 6. So I can only fix 2 more particles here. This is 4, right? 4 epsilon. So I only need 6 epsilon to get 10 epsilon, which is the total energy. So for that I need only 2 particles here. So n is equal to 2. G is equal to 3. Okay. So microstates will be what? As I have written, Ni plus Gi minus 1 factorial divided by Ni factorial Gi minus 1 factorial. Okay. So Ni plus J. Ni is for first one we will write first. Okay. that is n1 plus g1 minus 1 factorial divided by n1 factorial g1 minus 1 factorial into, because this is multiplied sign, n2 plus g2 minus 1 factorial divided by n2 factorial into g2 minus 1 factorial. Okay, so n1 is your 2 plus g1 is your 2 minus 1 factorial divided by 2 factorial and 2 minus 1 factorial into 2 plus 3 minus 1 factorial divided by 2 factorial into 3 minus 1 factorial. This is 2 to 3, 3 factorial by 2 factorial into, this is a 5 minus 4, 4 factorial by 2 factorial into 2 factorial. Alright, this will be what? This will be 3. This is 2 into 2, 4. Yeah, anyway, this is 4 into 3. This is 2. So 12 into 3 is 36 by 2, that is 18. So 18 is the number of microseconds. Alright, is it clear? Is that clear? Okay. Otherwise, you can, yeah, this is omega is 18. If you are asked entropy, ln, kln 18. Yeah. Otherwise, if you can solve, if you want to solve it proper way, okay, or 2 epsilon, 3 epsilon. Okay, let's see. So, 2 epsilon can give me like what? This would be 4. If 4, this should be 6. So it can be like this. Okay. See, we don't need to write everything here. You may be thinking I have to write all the 18. No. Just see how I'm writing it. This. So these are the possibilities for 2 epsilon, right? So 2 epsilon omega will be 2 epsilon is equal to 3. Now for 3 epsilon, what are the configurations? I'm not, see, this, this, then this, this, and this. So these are the configurations. That means, what does this diagram mean? Means for this, it can be this, 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 all. Exactly for that also, for this, all. So it is like mixture. Okay. So this, for this, you can easily see, it can be guessed that they will be what? Multiply. Isn't it? These are 6 states. For one state, this is one state, there are 6. For 3 states, there will be 3 into 6. That's it. Okay. So total magnitude will be omega 1 into omega 2. 3 into 6, that is 18. These are 3, 6, 3 into 6, 18. So S is equal to KB ln 18. Okay. 18 is the answer. That is number of ways to obtain 10 epsilon. Is it clear? There is another way which is a very long way. It's better to avoid that because that will take you too much time in exam. Alright, is it clear? Okay. And next question. Plus question number 5. Question number 6. An ensemble of non-interacting spin half particles. Ensemble of non-interacting spin half particles is in contact with a heat bath with a heat bath at temperature T Okay, and subjected to an external magnetic field. An external magnetic field. Each particle can be each particle can be in one of the two quantum states in two quantum states one of the two quantum states of energies plus or minus epsilon naught. Okay, mean energy per particle is minus epsilon naught by 2. So free energy per particle is how much? Free energy per particle is how much? Okay. And simple of non-interacting spinor particles is in contact with a heat bath at temperature T, subjected to an external field. Each particle can be in one of the two quantum states of energies plus or minus epsilon naught. Mean energy per particle is minus epsilon naught by 2. Free energy per particle. Again, spinor particles heat by temperature T subject to an external field. Okay, and is one of the quantum states is a plus or minus. Like each particle can be in one of the quantum states of plus or minus epsilon naught. So mean energy of the particle is already given. That is minus epsilon naught by 2. So free energy. Okay, let's see how to solve it. Again, there is a magnetic field here, external magnetic field. Okay, so whenever there is an external field, you just think about that concept we have done the previous, like the first question, spin up. We'll consider this as the positive z cap. Okay, spin up. Okay, so this energy will be what? Minus mu b. This is magnetic field B. Spin down, the energy will be plus mu b. Is that alright? Okay. Hmm. So this u1 is minus mu b is equal to, we can write minus epsilon, and u2 is mu b is equal to, we can write epsilon. Okay. Mean energy per particle is given. Mean energy per particle that is E by n. E by n will be what? Minus epsilon naught by 2. That's given in the question. Okay. Hmm. Now let's calculate if the particle can be in one of the states epsilon naught and minus epsilon naught. So if we calculate the average energy, that will be summation gi e to the power minus beta ei divided by what? Divided by partition function z. So summation that will be 1 into epsilon naught e to the power minus beta epsilon naught minus epsilon naught e to the power beta epsilon naught whole divided by e to the power minus beta epsilon naught plus e to the power beta epsilon. Okay, this is the partition function. So if I take minus beta epsilon naught common, that would be e to the power beta epsilon naught minus e to the power beta epsilon naught minus whole divided by e to the power beta epsilon naught plus e to the minus beta epsilon. See, if I divide 2 on both numerator and denominator, it will give me e to the power beta epsilon naught minus e to the power minus beta epsilon naught divided by 2 whole divided by e to the power beta epsilon naught plus e to the power minus beta epsilon naught whole divided by 2. So this is, if you see, this is your sine hyperbolic beta epsilon naught divided by, this is cos hyperbolic beta epsilon naught. So the whole thing is giving me what? Sine, because that is minus epsilon naught tan hyperbolic beta epsilon naught. Okay, this is giving me tan hyperbolic beta epsilon naught. This is my average energy minus epsilon naught tan hyperbolic beta epsilon naught. All right. Now the average energy per particle is given. Mean energy per particle is given minus epsilon naught by 2. So I'll just put it here. So minus epsilon naught by 2 is equal to minus epsilon naught tan hyperbolic beta epsilon naught. Right? This are cancelled. So 1 by 2 is equal to tan hyperbolic beta epsilon naught. Now what is needed? Beta epsilon naught is how much? Tan hyperbolic inverse 1 by 2. Is that right? Is it right? Yeah. Now what is? We don't need to write it. I just wrote it here. Now what is your free energy? Free energy is asked minus kT ln z. So minus kBT ln. What is z? Beta epsilon plus minus beta epsilon naught. Okay. So this is again what? Minus kBT ln 2 cos hyperbolic beta epsilon. Okay. And what is beta epsilon naught? This one. So I can just put it there. Minus kBT ln 2 cos hyperbolic tan hyperbolic inverse 1 by 2. This should be the answer. Is it alright? See, it's not hard. Is it hard? You just need a bit of practice to solve this kind of question. This is the formula for free energy. More and more practice is needed to solve this kind of questions, to have a practice, to have that fluency in this kind of questions. Alright? Next question, question number 7. Let's do an easier question this time. Question number 7. Total power emitted. The total power emitted by a spherical black body of radius r, spherical black body of radius r at a temperature T is P1. Let P2 be let P2 be the total power let P2 be the total power emitted by another another spherical black body another spherical black body, okay, of radius r by 2 kept at temperature 2T. The ratio P1 by P2 is how much? Okay, the total power emitted by a spherical black body of radius r is at a temperature T is P1. Let P2 be the power emitted by another spherical black body of radius r by 2 kept at temperature 2T. The ratio P1 by P2 is how much? Okay, how to solve it? Simple question. Power emitted by black body. Right now, power emitted by a black body is how much? P is proportional to a t to the power 4. Area, this is area, this is t to the power 4. So P1 by P2 is equal to A1 T1 to the power 4 divided by A2 T to the power 4. Now what is given? Spherical body of R by 2. This is R by 2 P1 P2. Okay. Temperature T to T. Okay. So P1 by P2 is equal to spherical body 4 pi r square. So r1 square divided by r2 square. This is t fourth divided by 2t whole fourth, because this is 2t is given. So r square divided by this one is r by 2 square, r square by 4 into t fourth by 16 t fourth. T4 gone r square on this 4. So the answer is 1 by 4. So the ratio P1 by P2 is what? 0.25. Is that clear? Is the question clear? Yeah. Next question. Question number 8. Question number 8. The entropy of a system, the entropy of a system of n spins, which may align, which may align either in downward direction, either in downward direction or in upward direction, or in upward direction. S entropy is given by S is equal to minus KVN P ln P plus 1 minus P ln 1 minus P, right? So where probability, P is the probability of alignment in upward direction, in upward direction. Okay. So the value, what is the value of P? What's the value of P for which the entropy is maximum? The entropy, for which the entropy is maximum. The entropy of a system of n spins which may align either in upward direction or in downward direction is this. P is the probability of alignment in upward direction. What is the value of P for which the entropy is maximum? For which the entropy is maximum. Okay, so here alignment doesn't contribute to that much because value of P for which entropy is maximum. So whenever this kind of questions come, what we usually do, we take the derivative of this with respect to the one that is asked and make it 0, right? So exactly we'll do that here. So answer S is equal to minus KBLN PLN P plus 1 minus PLN 1 minus P. Okay, so for S to be maximum, what will you do? Del S by del P is equal to 0. So del by del P of minus KBN P ln P plus 1 minus P ln 1 minus P is equal to 0. So minus KBN goes out. Del by del P of this one is, let me directly do it. P by P plus ln P plus 1 minus P by 1 minus P, and there will be minus ln 1 minus P is equal to 0, is equal to 0. So this goes to that side, 1 plus ln P minus 1 minus ln 1 minus P is equal to 0. 1 1 cancelled. Ln P by 1 minus P is equal to 0. Okay. So P by 1 minus P is equal to e to the power 0, isn't it? Is equal to 1. So P is equal to 1 minus P, which implies 2P is equal to 1. That means P is equal to 1 by 2. Okay. So the value of P is 1 by 2. 0.5. That will be the answer. Is it alright? I hope you understood this. Yeah. Question number 9. Question number 9. Consider a system of two particles A and B. Each particle can occupy each particle can occupy One of the one of the three possible quantum states quantum states one, two, three. The ratio of the probability the ratio of the probability that the two particles ratio of the probability that the two particles are in same state to to the probability that that the two particles are in different state. The two particles are in different state are in different state is alright. Consider a system of two particles A and B. Each particle can occupy one of the three particles possible quantum states 1, 2, 3. The ratio of the probability that two particles are in the same state, the probability that two particles are in different state. Okay, and you have to calculate for bosons and classical particles respectively. Okay. So for bosons, if you read the question, bosons 1, 2, 3. Okay, particles are in same state, the particles are in different state. Alright. So the bosons, how can they be arranged here? They are indistinguishable. So I can just make it like a small circle here, 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 and then two particles here. Got it? So this is one, two, three, 4, 5, 6. So six, total six. But how many are in same state? Ratio probability that like two particles different state. Like probability that two particles are in same state to two particles are in different state. So here probability of having same state is what? Same state is what? Same state. One, two, three. Total number of states six. 3 by 6. Okay. Probability of different state is what? One. Sorry. One, two, three. How many totals is six? 3 by 6. 1 by 2. So what is the ratio of this? Probability of same by probability of different. That is the question. Very good question. We have also done it in our statistical like classes. 1 by 2 by 1 by 2. This is 1. Okay. Now for classical, this is for boson. For boson, the answer is 1. For classical particles, classical for classical particles, for classical particles. Classical particles are what? Distinguishable particles. So again, one, two, three. Distinguishable particles, we can arrange them A, B, A, B, A, B. Yeah. A, B, A, B, A, B. Also the opposite. B, A, B, A, B, A. Right? Total number of states is 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 states. So same state, probability of same state like the previous one would be how many same states are 3? 3 by 9. Probability of different is 6 by 9. 6 by 9. So what is the ratio? The ratio is 3 by 9 by 6 by 9, that is normal. Okay. So for classical particles, the ratio is 1 by 3. Is it correct? Do you get it? Oh, sorry, 1 by 3 by 6, no, 1 by 2. Sorry, 1 by 2. Is that alright? Yeah. So, question number 9. Okay. Last question, question number 10. Okay. When a collection of when a collection of two level systems, two level systems is in equilibrium, is in equilibrium at temperature T naught, the ratio of the population in the lower and upper levels is 2 is to 1. When the temperature is when the temperature is changed to T, the ratio is 8 is to 1. Then options are T is equal to 2T naught, T naught is equal to 2T, T naught is equal to 3T, option D, T naught is equal to 4T. Collection of two level system is in equilibrium at temperature T naught. Ratio of the population in the lower and upper level is 2 is to 1. Okay, so when it is T naught, this is 2 is to 1. For example, this is 2, this is 1. Okay, but when it is changed to T, the ratio of lower and upper level becomes 8 is to 1. 1, 2, 3, 4, 5, 6, 7, 8. This is 1. This is 8 is to 1. When the temperature is T. Okay, so how will you calculate it? See, we know the like population formula is e to the minus e by kbt. Okay, so this is n1. N1 is what? E to the power minus e1 by kb t1 t naught. N2 is e to the power minus e2 by kb t. Alright. Hmm. Now, no, no, sorry. Okay. This is N1. N1 is for this state. N1. This is N2. N2 is upper level is e to the power minus e2 by kb t naught. So N1 by N2 is, you can see, 2 by 1, isn't it? So upper by lower level, like this one is lower and upper level is 2 is to 1. Na? So N1 is lower, this is upper. So N1 by N2 is 1 by 2 is equal to e to the power minus E1 by kb t naught, E2 by kb t naught. Okay. Exactly for this one also you can write N1 by N1 dash by N2 dash is equal to e to the minus E1 by kbt, E2 by kbt. Energy will remain same. The temperature is changing. This is 8 by 1. Yeah. Alright. So from here we can see e to the power minus E1 minus E2 by kbt naught is equal to 1 by 2. So minus E1 by E2 by kbt naught is equal to ln 1 by 2. E1 minus E2 by kbt naught is equal to ln 2. Okay. So E1 minus E2 is equal to kb t naught ln 2. Exactly here if we calculate same thing, E1 minus E2 by kb t is equal to ln 8, right? Now E1 minus E2. Okay, I'm going to start. E1 minus E2 is KB T naught ln2. Put it here. KB T naught ln2 divided by KB T is equal to ln 8. Yeah. KB KB gone. T naught ln2 by T is equal to ln 8. Okay. Now T naught by T is equal to ln 8 by ln 2. ln 8 I can write 3 ln 2 divided by ln 2 3. So T is equal to what? T is equal to 3 T naught. So T goes here. T, yeah. Oh, 3. Yeah. T is equal to T naught by 3. That means T naught is equal to 3T. That becomes. Alright. I hope you understood this and understood the questions that we did. These are very important questions that are usually come in GATE exam. So it's better to prepare. Right? Yeah. Thank you so much for watching and all the best for your GATE exam. Thank you very much.